Okay, so take a look at the 5.8 notes. All right, here we go. So the essential understanding says the degree of a polynomial tells you how many roots the equation has. So in a degree 1, let's go ahead and draw a little picture here. A degree 1 is a line, and that's going to cross the x-axis one time, okay? And it'll be at the x-intercept. However, if I have degree 2, which we did back in chapter 4, I could have 2 real zeros, 1 real zero, or none. And the zeros, the real zeros, are the x-intercepts, which we talked about. So let's write that down. The real zeros are the x-intercepts. We're going to skip example 1, and we're going to drop down to problem 2. Okay, we're going to skip example 1, and we're going to go ahead and look at problem 2. I'm going to give you an equation that is modeled from a data set that's been collected. And you might think, okay, who cares? Why would we want to do that? They're actually, in the real world, if you're in business, you actually collect lots of data, and then when you plot that data, and this is the cool part, I know I've mentioned to you that my husband is a ceramic engineer, and so they work with a lot of different companies that deal with like heating whatever their objects are. It could be bricks, it could be in the automotive industry, some of their parts that are ceramic, and they heat them. And so what they do is they collect the data and they plot it on a grid. And the computer plots it for them. But my husband, as the engineer, he has to look at what the dots are looking like. And so sometimes they've been logarithmic, which we're going to do in chapter 7. Or they've been exponential, which is in our chapter 7. Sometimes they're quadratic, sometimes they're linear, sometimes they're sinusoidal, which we'll get to in our chapter 13 this year. So even though a lot of times a computer will plot it, you as the person, if you're in business, you need to look at what is the trend. And can I come up with an equation for it? And the graphing calculators will actually do it for us. But let's go ahead and look at problem 1. Or excuse me, problem 2. It says, this is food production. So the chart shows how much milk Wisconsin dairy farms produced in 1955. So you see 16.5, and this is in billions of pounds, okay? That's a lot of milk production. And in 1980, the Wisconsin dairy farms produced 22.4 billion pounds. And in 2005, they did 22.9 billions of pounds of milk. So I give you the model, and I want you to go ahead and rewrite it. It is right here, but the calculator will do this for us. It actually came up, and I want you to notice this. Underline this piece. X is the number of years after 1900. So sometimes, because you don't want such huge numbers in an equation, so it's very common for people in whatever industry they're in, they'll say, okay, we're going to chop it off at this so that we don't have, the numbers would be enormous in the equation. It'd be hard to graph it, it'd be hard to work with it. So X is the number of years after 1900. So it says use this model, and a model is another word for an equation. It says use the model to estimate the milk production in the year 2000. So if X is the number of years after 1900, what would X be for the year 2000? I'm not going to put 2000 in there. But if X is the number of years after 1900, and I want the year 2000, what would X be? 100, okay? So I want you to take out a calculator if you have one, and we're going to plug in X is 100. And we want to find out what the approximate milk production was by the Wisconsin dairy farms in the year 2000. So you'll take 0.128 times 1,000, close that parenthesis, plus 10.36. Anybody have it yet?
Yes.
What'd you get?
23.16.
Okay, so let's say 23.2, and guess what? It's not 23.2, it's 23.2, and look at my units. They were billion pounds. That's a lot. And if you look at the data, so like if we plotted this on the graphing calculator, do you see that does look like a line? It does look like it's going on a line. All right, when you're ready, flip the page. And in example 3, I gave you some more data, and I'm going to give you, so on the quiz Friday and the test next week, I'm going to give you the equation, okay? But you're going to have to interpret it. So this, I like to take a moment and look at my chart. I have years, 1970, 1980, 1990, and 2000. This is the U.S. per capita egg consumption. Do you understand what's per capita mean? It's now per capita means either per person or per household. It's usually per person, per capita. So this is, so in a year, each person is consuming 302 eggs. And then you notice, it's kind of interesting because now it's down to 247. And it's just interesting what these surveys and research studies come out with. Because at one point it was like, eggs are good for you. Then they said eggs were bad for you. And now we're back to eggs are good for you. It's like, in my lifetime, they've been good, bad, and good again. So it's just kind of like, okay, I'm not quite sure what to do with that. But, all right, so here's my linear model. It says y equals negative 2x plus 431.5, where x is the number of years after 1900. What would be the egg consumption in 1995? So what would x be? 95. It's not 1995 because x is the number of years after 1900.
Oh, okay.
Okay? So now you're going to use your calculator and you're going to plug into the model that I gave you. And anybody got it?
241.5.
Good. So it's 241.5 eggs
Ew.
per capita, per person. Okay? All right, now we've got a definition here, and it says, using a model to predict a y value outside the domain is called extrapolation. So if you are taking your model and you have a table of values and you're now taking it beyond the collected values, domain are the collected x values, that's called extrapolation. If you use your model to predict an estimation within the domain, it's called interpolation. And it says extrapolation is really less reliable the further away you get from your data. So let's look at example 3. And if I'm looking at 1995, is 1995 within the collected data or beyond it? Within it. So let's go back and write that this is interpolation. Okay, this is an example of interpolation. Let's flip and go back to the front side. And example or problem 2. Let's look at the data collected. The data collected was 1955, 1980, and 2005. We found it for the year 2000. Is that within the collected or beyond it?
Interpolate.
It's within it, right? 2000 is in between 1990 or 1955 and 2005. So this is interpolation. An example of extrapolation would be like 2018. Yeah.
I think being clear enough to go to
No, it's not till like 43, I think. Yeah, no, you're fine. Okay, let's look at the very last one. Okay, we'll get this one in before the bell. It says you're given the following data. The U.S. federal spending. So I have 1965 to 2005, and the total is in billions of dollars, okay? So here's now, this is a much more complicated model. It's y equals 0.028x cubed minus 6.711x squared plus 578.194x minus 16226.667. It says estimate the total U.S. federal spending in the year 2000 if x is the number of years after 1900. So 2000, the year 2000, how many years after 1900 is that? 100. So watch what you're going to do. This is going to be y equals 0.028 times 100 cubed. So this is where a graphing calculator is helpful, but it will still work on a red OGT if that's what you've got.
what?
The red OGT calculator.
What kind of number? 16266.66676.
It's not so weird. That's 162,000, or no, 16,226. Not so weird.
Money?
Look, yeah, it's money.
637 billion money.
And this is billions. So that's actually an enormous number. And since 2000 is within the collected data set, that is an example of interpolation.